In this video, we'll talk about an introduction to Faraday's law. So when we talk about Faraday's law, try to keep in the back of your mind here the law, of course, that we've been using in some other videos called Lenz's law. Try to keep that in mind. Lenz's law. Because what Faraday's law really is sort of a mathematical ramification or mathematical rendition of Lenz's law. Let's take a look. So the first thing you have here is you have this side here, which is that script E again. This always stands for EMF, or electromotive force. So the way you just think about this is just good old volts. Okay? So Faraday's law is a mathematical law that tells you basically where volts comes from, or how one way you can get volts. That's what this side gives right here. Now you see the minus sign right here. This is the ramification of the word opposes. Opposes, which is in Lenz's law. Remember, induced currents are always in the direction to oppose changes in external magnetic field or flux, whichever the version you have. So that's sort of what that means. That's what the minus sign is right there. The next thing we have here is we have a time derivative sitting here. It's a d by dt of something, and the thing you're taking the time derivative of here, this quantity here, this is the magnetic flux. Okay? This phi sub b, capital phi sub b is magnetic flux, and Faraday's law instructs you to take a time derivative of it here. So the time derivative sitting in here, this is the mathematical ramification of the word change. That's in Lenz's law also. Because you are taking a time derivative here, say a d by dt of something, and the thing that you're taking the derivative of here is a constant, then you'll just get 0. So if something isn't changing, you'll get 0, and if you get a 0 for this, there's no EMF, everything's over, there's no induced current, everyone can just go home. So it's looking for a change here. So you see all the elements of Lenz's law are there, and also what's nice about Lenz's law, it also sort of firms up what are we actually worried about the change of? Is it magnetic field or something else? And in the case of Faraday's law, it's very clear now. It's actually the magnetic flux. It's not the magnetic field or a bunch of lines. It's the magnetic flux that we're interested in the change of. So the time derivative of magnetic flux with a minus sign gives volts. That's essentially what Faraday's law is. And you see all the two key things of Lenz's law in there. In particular, there has to be a change and something has to be opposed. So with that in mind then, let's go ahead and look at some examples of Faraday's law. But let's just get a little lesson here on what that magnetic flux term is first. So phi sub b, uppercase phi sub b, this is magnetic flux. Okay, so what does it refer to? Well, the definition of it, probably the best one to think of here, is that it's magnetic field times some area times the cosine of the angle between the B field and some area. Okay, so this is probably the most obvious term here. You know what that is. That's the magnetic field. And this one right here, this is the area of some loop. Now, what loop are we talking about? Well, if you go back and look at watch through the Lenz's law videos again, or read your book on Lenz's law or whatever, there's always a bunch of loops in those problems there. There's loops about, like sort of there might have been a circle sitting like this, which is a loop here, and there might have been a magnetic field like this, which was increasing. We always ask for what would the induced current in the loop be. So there's always these loops in there, and now is the time where that's going to sort of come to play here. This is when the area of the loop here. Alternatively, the way you can sort of think about this here, this is sort of the area that contains the B field. So there's a few ways to think about that as well, because again, if you go back to some Lenz's law problems, we saw problems like this, where here's a B field like that, and maybe the loop was entirely immersed by that B field. Something like this. Here's the B field, here's the loop. So this entire loop here contained magnetic field lines. If I draw them back in now again, the entire loop contained magnetic field lines, and so of course the area in the magnetic flux would be the area of the entire loop. But then there's some Lenz's law problems where you have a loop like this, and the magnetic field might only be at a small region interior like that. So although there is a loop here, and this might actually be a real piece of wire going around, the magnetic field is sort of constrained to just this small area inside of the larger area. So this would be what I mean by the area that contains the magnetic field. So in this case here, just coincidentally, the loop itself contains the magnetic field, because the magnetic field area is much larger than the loop. So the loop itself contains the magnetic field. So the area is just the area of the loop. But over here, the area of the loop in question might be this black one here, sort of on the outside. But because the magnetic field area is so much smaller, then this would be the area in the Faraday's law. So be careful with that. Area that contains the magnetic field can be the actual loop itself, or some fraction of it. And of course, the last item right here is theta right here. Theta here is the angle between B and A. Angle between the magnetic field and the area. So the direction of the magnetic field in terms of figuring out this area is usually pretty straightforward. The direction of the magnetic field well, the magnetic field is usually drawn with a bunch of arrows and stuff. This one's probably pretty easy to find. Well, what is the direction of an area? Well, the direction of an area is always normal to the area. There's some little arrow you can draw that's normal to the area. So for instance here, if I have a loop like this, where's normal to the area? Well, it's going to be a little vector that looks like this. And if I have a square that's maybe pointing this way here, where's the normal? Same sort of thing, arrow that points like this, but there's always a little 90-degree angle in there. So these sorts of situations here, these are always the normals. Then you go, well, wait a minute, how do I know that the normal is not down, not up like that? So how would I know that the normal, instead of pointing up, isn't an arrow that's going to point down like this over here, or down like this over here? Could be confusing, but I just looked on Wikipedia about the vector area and what they sort of said there, and this is the commonly accepted thing. You take your right-hand rule, and you imagine your palm of your hand is going to touch these loops. And if you scan your palm around the loops like this, the normal is always going to be in the direction of your thumb. So I am right then to draw these arrows the way I have drawn here. If my palm touches the loop all the way around, my thumb points up, that's the direction of the normal here. So this would not do it, the red one right here. Same thing over here. If my palm touches the loop and I go around like that, thumb points in the direction of that arrow up like that. So the normals here, maybe we can call it here, is sort of the right-hand normals. Let your palm drag around the outside of these areas here, and your thumb will always point in the direction of the normal like that. So in either case, we can always get the direction of an area that way. Okay? So how do I put all this together here to consider what magnetic flux is? Then we'll sort of get ourselves back on track to look at some Faraday's law examples here. Is that, well, let's just say I had a magnetic field pointing this way. Here's a nice B field for sake of our illustration here. And what we'll do then is let's put a loop in it. And I'll draw the loop so the thick side sort of points towards us like that. And the back side is going to be like this. It's going to go around like this. Sort of try and draw a nice, neat loop for you here. And let me just make sure, for our sake of our perspective here, that these blue lines are sort of on top like this, like this. So we know that this is the edge that's towards us here. Now we want to draw the normal to the area, because we see the direction of B is clearly to the right. Now we need the direction of the area. Well, again, if I touch this outer rim with my palm of my hand here, so all the way around, I see my thumb points this way. So it looks like my normal is going to be over to the left there like this. And that's just fine. So here's my normal like that. I'll just sort of draw as the area right there, nice and perpendicular. So there's my area like that. So look at what I have. Well, if I look at what I have now, I have the magnetic field towards the right, the area towards the left. That sort of gives me a theta here of 180 degrees. And the cosine of 180 is -1. So it turns out it's not all critically important in Faraday's law with flux to be too concerned about these areas in cases like this, because the point is that this is sort of a relative maximum for the cosine here. So remember that the cosine of 0 is 1 degree, the cosine of 180 is -1 like that. But in either case, it's sort of like these are sort of the extrema that the cosine can achieve there. So what we're going to say here is that the flux will also be an extrema, because I have either a 1 or a -1 for my cosine right there. And there'll always be some magnitude of the magnetic field. I don't know what it is. Someone is Tesla or so, the strength of those blue lines there. And now this area here is actually the pi r squared of this loop here, the area of the loop right there. So you see I have all the elements coming together. So in either case here, the flux in this particular configuration here is a relative maximum right here, because I have a lot of magnetic field piercing a lot of the area. Okay, the area points the other way in this case here, so the cosine of 180 is -1, but we still have a relatively large amount of flux going through the loop, and maybe I'll even consider in some cases here, just give me the relative magnitude of the flux, even take the absolute value there. It'll be a relative extrema. Now what do I mean by all I keep saying relative extrema and that sort of thing? What does all that mean? Well, let's just draw the same system again. Here's the magnetic field. Like this, that's sitting in there again. Let's draw the loop in a slightly different orientation. Let's draw the loop so that it's looks like this. Here's that leading edge nice and thick again like that. There's the other one going around like that. And let's say that the normal to the area is up like this. So again, if I let my right hand sort of drag along the outside, thumb points up like that, there's the area. So now if you look at what you have here, the angle here between B and A is 90 degrees. And what we know, just from, of course, basic trig, the cosine of 90 is 0. So in this case here, the cosine of 90 being 0, the amount of flux through this loop is actually 0 also. There's no flux through the loop. So you can sort of see the two cases here. When I had the loop oriented like this, my flux here was sort of maximum. And when I turn the loop by 90 degrees, the flux becomes minimum like that. And yeah, you guessed it, all the cases in between exist in there as well. If I sort of put the loop so it looks like this, and the normal's up like that with my right hand normal, there's an area like that. So now what I have is the angle between the magnetic field and the area is something like this. So here's a magnetic field line, and I'll get an angle right in here. There's my theta now. There's my theta now, maybe something like 45 degrees. So see, depending on the angle and the orientation here, I can get varying amounts of flux, maximum flux, zero flux, flux somewhere in between. So you should sort of think of flux as how many of these magnetic field lines can the area possibly capture or pierce. So maximal capture right here because you have whole area facing those magnetic field lines head on. Zero flux here because the magnetic field is sort of skirting over the area without actually piercing it, no flux. And some intermediate results in there because it'd be more optimal to be aligned like this. So there's a very common analogy for this. If you imagine the magnetic field lines like wind coming from a fan, you'll get maximum wind in your face if you just face the wind head on like that. Like this is your face like this, you get maximum wind in your face and maximum cooling. But if you wanted to cool off in your face, well, the perception of cooling is different for everyone here, but you wouldn't get as much direct exposure to the wind if you sort of let it just gloss over the surface of your face and off. Now, it might cool you off and it might feel good, but you're still not feeling the full brunt of this wind here. And of course, for your face to be at some intermediate angle in between there, you can get varying amounts of wind hitting your face. So flux is sort of like that. All right, so now, what does that have to do with Faraday's law? Well, here we go. Let's get those examples out for Faraday's law. There's your magnetic flux idea right there. Okay, so Faraday's law looks like this. Faraday's law, once again, said that induced EMF is the time derivative of that thing called flux. And if we remember now, flux is B times A times the cosine of the angle between B and A. So we'll get our clues here about where voltage comes from. Let's just go ahead and do the time derivative then. So if we take the time derivative of flux, like this, big product rule to assign here. These are like three things, all of them could possibly depend on time. So we have to be careful how we take the time derivative. So it can be a dB dt times A times the cosine of theta. This is certainly one of the product rules here. The next product rule we could have in here would be plus B times dA dt times the cosine of theta. We could have a time derivative like that. A could be changing. Again, I'm just applying the product rule here, which says it's the time derivative of this, times the time derivative of this, times these two, times the time derivative of this, times those two things. Just the product rule. And the last case here, so I can have B and A, and derivative cosine is minus sine. Now to even apply the chain rule one additional time because the angle could be changing here, so I have to have sort of a d theta dt in there. So this is really the epitome of Faraday's law, and we'll wrap up the video by showing you a few individual examples of these here. So there's three ways I can get a d phi b dt. Three ways I can get this to be non-zero. Now why am I concerned with the time derivative of flux, the d phi b dt? Because that's what goes over here in Faraday's law, and if this is non-zero, that's where I'll get my volts from here. So I'm sort of concerned here with what do I have to, in what ways can I get some voltage out of Faraday's law? How will that work? So, all right, so we take a look at the system here, and there's three ways. The first way right here is I can have a non-zero magnetic field. In other words, B can be changing. I could be getting some changing B. And we saw that in the videos on Lenz's law, that when we change the magnetic field, that induced a current here. So here's the explicit representation of it. dB dt. B could be changing. In sort of an odd case over here, area could be changing too. Area changes. That's another way of getting a non-zero term. And of course, in the last case over here, what could be changing? That angle can change. And what theta, remember what theta is? Theta is the angle between B and A. So if the angle between B and A changes, that will give a non-zero term. So the point I'm trying to get here is, when is this non-zero? And why am I concerned with this? Because that will give me a non-zero voltage. There's three cases, three different ways this can be non-zero. The magnetic field can change, the area can change, or the angle between B and A can change. Those are the three ways Faraday's law will deliver some voltage to us. Let's look at the three cases now. Just some quick examples here, and we're going to wrap this video up. It's getting kind of long here. Okay, so Faraday's law. Okay, the first case here involves dB dt. We've seen cases like this before now, where you can have a loop of wire like this, and you can have a magnetic field sort of in the region in and around this wire like that. Here's your B. So of course the straight Lenz's law model say maybe this B is increasing or maybe this B is decreasing. In either case, those increases or decreases gives a non-zero dB dt, and that will give rise to an induced current in this loop. That's one way that gives an EMF. So remember, the induced current is one way, but where do currents come from? Currents come from voltages in wires and electric fields on the internal to those wires there. So that's sort of where those voltages come from. And so Faraday's law addresses directly the electromotive force, which is ultimately what's responsible for pushing electrons through wires. Okay, so that's case one, the dB dt. Number two we saw is you can have a dA dt. The area can be changing. And so it's a case like this now, where here's a magnetic field. And say here, we'll just isolate the case here and say, well, this magnetic field is not changing here. Over here, maybe it was going up or down, but here, let's just say the magnetic field is constant. So what we can do is, I don't know exactly how you'd pull this off, and maybe you have some rubberized metal, but then maybe it wouldn't be metal if it's rubberized and vice versa. But you can have a really small area like this, and then what you could do is you could cause this little loop here suddenly to just start expanding. You could make it go out like this, some breathing motion, some out like that, and maybe in again, and out and in. In either case, if the circle got larger or smaller, you'd have to agree that the area of it was changing. And if the area of it's changing, then Faraday's law says you're going to get an induced voltage because the area is changing. So you can just imagine this thing just getting bigger. So I'll just draw some arrows on this here. So if it's sort of expanded like this, then A would be increasing like this. A would be going up, and that means dA dt would be some non-zero values. That's sort of the simplest way to think about it. There's one other way, and this way you might actually see in your physics book here some sort of common problems that you might see. Imagine there's a magnetic field like this. Just fill some region space here, and again, it's constant. I'm not going to deal with the case here where the magnetic field is changing. This is the constant case here. And you might have a loop in here, sort of a U-shaped piece of wire that looks like this. And the way the problems are often phrased here is then you have a movable piece of wire, something that can slide sort of like this. So it can slide like this. In other words, and maybe you're even pulling this piece of wire this way. So if you look very carefully, what you have here is you have a current path which sort of goes around like this. It can travel through this wire and up around here. The current can go around like that. But if this slidable wire is moving this way, then the area of this loop inside the wire is increasing. In fact, if you're sliding it that way with a speed v like that, and this is some width right here, and this distance here is x, then the width at any given time, or the area at any given time, is just w times x like that. But remember now, if you want to know what dA dt was, what is the time derivative of the area? We're not so interested in the area, but if it's changing in here, that would be something like the width times dx dt, but dx dt is just v. So width times v then is going to be the change in this area here, and that's exactly what can go into Faraday's law once again to give an increasing voltage. So I hope you can see that as this wire here slides to the right, the area increases. As it slides to the left, the area decreases. But that's a current loop whose area is changing. Probably a little more concrete example than that rubberized loop I draw there. So that's number two. Make a little room here. So we cover the dA dt. And the last one here that is sort of the real important one for some practical applications here is we saw theta can have a change. D theta dt can change. So the angle between B and A can be changing. Okay? Let's look at the case like this. So here's a magnetic field. It's going like this, not changing. So what if we put a loop in that wire in this magnetic field, pardon me. So let's say we put a loop here, look like this. Here's that thick edge like that, and here's that thin edge that goes back into the plane. Let me firm this up a little bit like this. There we go. There's a loop in there. And suppose what we did is we put the loop here on an axis of rotation that maybe looks something like this and this. And we caused this loop to spin like that. So we took the loop in there and we just made the loop start spinning. So I have a little model I can show you like that. It looks like this. Here's my wire loop here. Here's that magnetic field like this. So suppose the loop is in here and I just started spinning this loop. Just started spinning like that. You'd have to agree now that the angle between the loop and the magnetic field is changing. So if here's the normal or the area to this loop here, I'll try to sort of put this marker here in the direction of that normal like this. As this thing starts to spin like this, that normal changes too. And if that normal changes its direction, then the angle between the magnetic field and the normal will change also. That is a change in theta. That d theta dt will be non-zero in the case like that. And so you can get a voltage in that case too. Now, the reason why these cases are so important here is because these are exactly where generators come from. So we'll reserve a different video to talk about generators, but these are the three cases of Faraday's law. You're looking out for a changing B, a changing area, or a changing angle between B and A. Either one of those will give a non-zero induced EMF.